Okay, do you have any questions before we start? About the homework or the things we did 2 weeks ago?
Can we get a 4-hour extension on homeworks?
Why do you want 4 hours?
Mesai bitimine denk düşsün istedim.
Okay.
Is there any update on the Wednesday lecture?
Now, for the Wednesday hour, the only suitable hour seems to be at 14:40.
Today?
No, on Wednesday.
On Wednesday.
Yeah.
Okay.
If it will make any difference for you, we can shift it for 1 hour. But I don't know if it makes any difference. Well, one thing we can do is let's just wait a couple of more weeks. You see, there are some students who are registered who don't show up. And after a couple of weeks, we can just have a vote in class. Other questions? Okay, so let's start with statistics. In fact, before that, let's look at big numbers, because basically that's what we will be dealing with. Now, when I say big numbers, we won't be dealing with numbers of the order of, let's say, n, which is of the order of 10 to the power 23. But most of the time, the numbers we will have will be of the order of 10 to the power n. These are the things that we will calculate. And of course, we will take the logarithm to make it a more manageable number. But before taking the logarithm, the quantities that we will evaluate will be of this order of magnitude, all of them. Let's say, what order of magnitude of an error would you consider a big error in your computation, typically? 15%?
15.
15, a factor of 15, okay.
10 to minus 4.
10 to the power minus 4 is a big error for you. A factor of 5 is a big error for you. Let's say that we make a mistake in our computation that is of the order of n itself. This you would probably consider a huge error, right? Well, let's see. Let's take the logarithm of this number. Eventually, we will be taking the logarithm of whatever we calculate. Well, this is n plus logarithm of n. This is 10 to the power 23. This is 23. I can just ignore it. So basically, n times 10 to the power n for us will be almost the same as 10 to the power n. So even if we make an error in our overall factor that is of the order of n, well, that will be a small error for us, negligible even. Well, of course, 2 weeks ago when we were discussing, you were asking about what happens if we apply these things to particles with, to an electron or to a single spin. Of course, this doesn't work for such small numbers, but for huge numbers, numbers of the order of 10 to the power 20, 10 to the power 23, well, such mistakes are, well, negligible. Now, this will be important whenever we are, let's say, calculating summations. Well, most of this course will be about how to calculate certain sums. And at least for some of them, let's say, these numbers, well, there will be at least one among these, which is of the order of 10 to the power 10, 10 to the power n. And the other numbers will be much smaller. We will be looking at distributions which will look something like this. Almost a Dirac delta, but not a Dirac delta. Well, how many such terms we have in the summation? Well, it will depend on the summation, but let's say typically there are a huge number of terms in this summation that whose value is of the order of 10 to the power n. A huge number would be, let's say, n terms, each of which has a value of 10 to the power n. So this summation will have a value of n times 10 to the power n, typically. But we just said that this is nothing but 10 to the power n for most practical purposes, which is nothing but a and 0. So basically, Whenever we have a sum, even if we have many terms in that summation, the final result of that summation will be equal to the term that has the maximum value. You see. Let me write it in this form. It is, if you look at this distribution, it's somewhere over there. So these are some of the tricks that we will be using. Well, we will make many errors in our computation as long as they are not of the order of 10 to the power n. They will be negligible. We will just keep our result correct up to factors of n. And whenever we have summations, of course, first we have to show that the typical term in that summation is, not the typical term, but some of the terms in that summation has a value of the order of 10 to the power n. In that case, whether you sum all the terms or take the term that has the maximum value, it won't make any difference. Well, and another result that we will be using is we will come to this point later on. Basically, if you would like to calculate the volume of an object, well, the volume will be mainly given by the surface area. Why? Well, let's see. What is the surface area of an object? Or what is the change in the volume? This will be the surface area times the thickness well, the thickness is just some reasonable number, not a huge number. So the surface area will scale as 10 to the power n. Well, this will be nothing but the surface area for all practical purposes for us. Well, the volume is nothing but sum of the incremental volumes. Well, we just said that this sum is nothing but dominated by the largest volume, largest increment in the volume, because the numbers will be 10 to the power n. And this is nothing but the surface area. Of course, in all these steps, we are making errors. We are introducing errors as overall factors, which will be typically, let's say, n. They will scale as n, the number of particles we have. But such errors, especially when we take the logarithm eventually, will be basically negligible. So, any questions here? These are just some weird properties of such huge numbers.
Thickness isn't always small, right? Obviously, it's object dependent, right? Thickness is not always.
Well, let me come to this. Let me come to your question when we discuss the ideal gas. We will calculate whatever volume we have. There will be a volume in phase space. The thickness will be basically the error in our energy measurement. It won't be very small. It won't be very huge. So in those cases, all these approximations will not lead to any practical differences, errors in our final result. Here I'm not talking about the volume of our three-dimensional sphere. Now let me first describe phase space. We will be, I think, this week, we will be talking about phase space throughout this lecture, practically. Now, typically, when we say phase space, we mean the space of all the momenta and coordinates of a given system. So if you are imagining a three-dimensional space, there are 3n coordinates of momentum plus 3n coordinates of position. And so our phase space will be 6n dimensional. Well, in a vague sense, we can still call the phase space the space of all quantum numbers. Specifying the microstate of a system. Now, the question we will be asking throughout this course is, given a macrostate, well, what we mean the macrostate, we know the pressure, we know the volume, we know the temperature, we know the total energy, and such a handful of parameters. How many microstates? These will be, let me use the classical description for the time being. How many microstates correspond to macrostate? This is what we will be asking. Now, we won't be changing all the parameters in the macrostate, but let's start with saying we only have a single variable. We have chosen our system. The pressure is the volume is fixed. The volume is fixed. So let's look at the energy. How does this number change with the energy? So I will define this quantity. This is the number of microstates having energy E. Now we will be calculating this number for the ideal gas. Now, of course, the first problem we are facing is, first week we discussed that eventually we would like to calculate the thermodynamic properties like the temperature, the entropy, the free energy, etc. So how is this related to, how can we relate this to our thermodynamic properties? Now, let's look at a system made up of two parts. The left-hand side will have, let's say, the whole system has energy E. Let's say that the left-hand side has energy E1, the right-hand side has energy E2. Of course, E1 plus E2 will be E. So we have this two systems that can exchange energy. Now, we have already studied such systems in thermodynamics. So we know that eventually the system will come to equilibrium when the temperatures are equal. So from a thermodynamic perspective, the total entropy of the system will be the entropy of the first subsystem plus the entropy of the second subsystem. We know that in equilibrium, entropy will be maximized. Let's say E1 and E2, they can change. The system can exchange energy. The total E is fixed. But let's see how the change in E1. What will that tell us? Well, this is ds by dE1 plus ds by dE2 times dE2 by dE1, and when the system reaches equilibrium, this should be 0. Entropy is maximized when all the changes happen. Well, this is -1. So this tells me that ds over dE1 should be, this is S1, sorry. This is S2. The two systems can have different expressions for the entropy. ds1 over dE1 should be equal to ds2 over dE2. Well, basically, you can just repeat this exercise for whichever subdivision you imagine. So this basically tells me that ds over dE for any subsystem making my whole system, let me put S over here, this is the entropy of that subsystem, its derivative with respect to the energy of that subsystem, this should be constant. Well, we know that the ds by, you see, dE is TdS. Volume is constant. I'm not allowing the volume to change, so the only thing that can change is the energy and the entropy. Well, this tells me that ds by dE is just 1 over T. So the maximization of the entropy already tells me that when these two subsystems are in equilibrium, they are inverse temperatures. Have to be equal. So maximization of entropy already tells me that the system should have a uniform temperature. Well, let's come back to this microscopic picture. So now let's imagine I have these two subsystems. They can exchange energy. What do you remember about probabilities? What is the probability let's say the probability that I will observe, let me say, the left-hand side to have an energy epsilon 1. What is this probability? How do you define the probability of anything?
Zero.
If you would like to be formally more correct, let me put it this way then. But let me ignore that one for the time being. It's not zero. Well, how do you calculate the probability of anything?
1 minus the complement, like
Okay, you are expressing probability in terms of another probability. You see, let's say you are flipping coin. What's the probability that you will get heads? How do you calculate that probability?
The total number of microstates in energy E1 divided by the total microstates.
The total. So you calculate the probability as, well, the general definition of that probability is the number of outcomes you want divided by the total number of possible outcomes. So this is how we define the probability of anything. Now, what is the probability that the left-hand side will have an energy epsilon 1? Well, this probability is the number of microstates in which E1 is equal to epsilon 1 divided by the total number of all microstates with total energy E. This is a probability. Well, what is the number of microstates in which the left-hand side has energy epsilon 1? Well, let me call that number omega 1 epsilon 1. Omega 1 is the number of microstates of the left-hand side. And so this is the number of microstates in which the left-hand side has energy epsilon 1. Well, I have to multiply this with all the number of microstates in which the right-hand side has the remaining energy. You see, even if the left-hand side doesn't change, if you change the right-hand side, you are getting a new microstate of the whole system, and that is one of your possible outcomes. So that's why we have this product. And the total number of possible outcomes will be this. Now, we will calculate this explicitly later on, but as with most of the probabilities that we will calculate, this has almost a Dirac delta shape. So now I can ask you the question, what is the most probable epsilon 1? So the most probable value of the energy of the left-hand side that I will obtain, how can I calculate that? Well, let's see. If I want to calculate the largest probability, this should be 0, which tells me that this derivative should be 0. Well, I'm ignoring the numerator because it's just a constant. It doesn't depend on epsilon 1. Which tells me that, let me call this number epsilon 2. I'm just using, sorry. This is d omega 1 divided by d epsilon 1 times omega 2 plus omega 1 times d omega 2 by d epsilon 2 times derivative of epsilon 2 with respect to epsilon 1. This should be equal to 0. Now that is minus 1. D omega 1 divided by d epsilon 1. Let me also divide both sides by 1 over omega 1 omega 2. D omega 1 by d epsilon, so that here I have 1 over omega 1 plus 1 over omega this is minus 1 over omega 2, the derivative of omega 2 with respect to epsilon 2. This should be 0. Derivative of logarithm of omega 1 divided by with respect to the energy should be equal to the derivative of logarithm of omega 2 with respect to the energy. So this is constant throughout my system. So just take any subsystem of your system. The most probable state is the one for which this derivative is constant, the same throughout my system. So if you, at the moment at least, if you take my word that this will be the probability distribution, it might happen that at the moment you see that your system is over here. Or let's say you just brought them in contact at some given time and you just measure the energy. Well, there haven't been enough energy exchange yet. So you measure an energy somewhere over here. This tells me that if your left system has that much energy, as time goes on, well, it will come over here. The most probable evolution of your system will be for which it will come to this point, epsilon max. Well, that basically tells me that if you observe the energy of your system to be at this point, it's not yet in equilibrium, it's changing. But let's say that you waited long enough and you observe that your system is over here already. If you measure its energy at some later time, well, most probably it will still stay there. If you keep on measuring, most probably it will still stay there. That means that the system is now in equilibrium. So it's just the most probable, when the system reaches the most probable configuration, well, it will just stay there.
Doesn't it fluctuate? Doesn't it?
We will look at the fluctuations. It will turn out that the fluctuations are of the order of 1 over square root of n. And keep in mind that n is 10 to the power 22, 23. So that is 10 to the power minus 11. So if you want to observe a significant fluctuation of this, well, such a fluctuation doesn't tell me that it will never happen. The only thing it tells me is that if you want to make sure that you observe such a fluctuation in your system, of fluctuation that is larger than this one. It is still possible, but typically you will have to wait for a time that is longer than the age of the universe. So for practical purposes, although we are talking about probabilities, the most probable states, etc., you won't be observing any deviation.
This is also the state of maximum entropy, right? Since we define it as
Well, you see, we didn't yet relate it to entropy. But we already have two things. On one hand, from this statistical probabilistic interpretation, we say that this quantity, if we have two subsystems that can exchange energy, I don't know how they will exchange energy, but let's say that they do exchange energy randomly. If that is the case, when the equilibrium is reached, this quantity will be constant throughout my system. Now we are talking about physical systems. Thermodynamics tells me that these two systems can exchange only energy. If we have two such systems in contact that can only exchange energy, when the equilibrium is reached, ds over dE is constant throughout the system. Well, you probably see the similarity here. You see, epsilon was the energy of the subsystem. Well, if you look at your book says that this also means that the change in the logarithm of omega with respect to entropy, this should be constant. Let's call that constant 1 over the Boltzmann constant. So the entropy, let's say, is defined as the Boltzmann constant times logarithm of omega. Well, you see, this tells me, this equation over here can at most tell me that the entropy is the Boltzmann constant times logarithm of omega plus some other constant. This is the most general relation between the two that satisfy this relationship over there. But you see, the third law of thermodynamics already fixes what that constant is. That constant should be 0 by the third law of thermodynamics. So this is the relation. This is the relation we have for between the statistics and the thermodynamics. Well, this already tells us why the second law is satisfied. You see, what we did over here, we asked ourselves the question, what is the most probable state? We already said that the system will evolve. The evolution will be very complicated, but it will always evolve to some more probable states. Well, if the system evolves to more probable states, you see, omega, the total energy is fixed. Let's say epsilon 1 is variable, the subsystems can change energy. And we said that this is just omega 1, epsilon 1, omega 2, epsilon 2. Now the entropy, this definition of entropy already says that it's an additive quantity. If your system is made up of two subsystems, the total entropy of your system will be just the sum. And if at a given instant epsilon 1 is not at its most probable value, we just have discussed over here that epsilon 1 will evolve into the more probable values. That is the most probable evolution of my system. It will be evolving to more probable values of epsilon 1. But as it moves to more probable values of epsilon 1, the entropy of the system increases. That is the most probable evolution of my system. Well, I will be dropping this most probable because the probability of that to happen will be 1. And the probability for my system to go into states with smaller with a different value of epsilon 1 will be 0. because it will be some finite number divided by an infinitely large number. That is why it will be 0. Any questions?
We're neglecting fluctuations because of system size, but this only holds for ideal systems, right? Like, when do fluctuations become important enough? that
We
can't assume
will see that when we look at.
interacting systems, right?
No, this is for any system. You see, the only time the interactions will become fluctuations will become important will be when we have phase transitions.
Okay.
That will be the only case where the fluctuations will be important.
Do they become independent of n? Or
Well, I mean, for example, if you are asking me what is the number of particles there, it doesn't become independent of n. If you ask me the average energy, that will be independent of n. Let's do an example. Most of the time, whenever we are studying a new method, we will be looking at the ideal gas. Let's look at the classical description. We know the energy of the system. Let's say the system has a total energy, E, which will be given by 1 over 2 mi/pi squared plus, oh, that's it. Just a bunch of particles with masses mi, then each one has a momentum pi. Well, let me define a different momentum, capital P, as square root of mi/pi. So the energy will be just this one. Or now in that summation I have 3 n terms. I have n particles, each one has 3 components of pi, so there are 3 n terms over there. Well, this is nothing but the equation of a sphere in 3n dimensional space. Now, classical physics doesn't really tell me how many microstates I have, but it does. I mean, you can kind of guess that, well, this is a sphere. The larger the area of this, the larger the surface area of this sphere, I should have a larger number of microstates. And also keep in mind that this is not the only definite restriction I have in my phase space. I have Qi should be within my volume V. So these two equations define the available region in my phase space. Well, this basically defines some kind of a hypersurface for me. So those are that is the surface where my system is allowed to be. My system cannot be outside, but it has to be inside the surface. And counting will be problematic. We will come to that later on. But at least you probably agree with me that the number of microstates will be proportional to the surface area of this hypersurface. The larger the surface area, we would expect a larger number of microstates. Well, quantum mechanics will solve this problem due to the uncertainty principle. It will tell us that not every point gives us a distinct microstate. Only if the points are separated by a finite volume, in that case, we will definitely be able to say that it is a different microstate. But that will come later on. So the number of microstates will be proportional to the surface area in phase space. Now, rather than calculating the surface area will be difficult to calculate. I will say that this is equal to, let me call that E plus dE where the sigma of E is the volume in phase space of microstates having energy less than or equal to E. This will be easier to calculate. But if I can calculate this one, well then I'm happy with I can calculate the surface area. So I changed my problem from what is this surface area to what is this volume. Well, the volume in any space will be nothing but the integral of the volume element. It will be the 3 n-dimensional momentum and 3 n-dimensional position integral restricted by these conditions of 1. So if you evaluate this integral over any finite volume, well, you will get the volume of your subspace. Well, there are no restrictions on Q. The only restrictions on Q being that they have to be within my volume V. So the volume integral will just give me V to the power n.
So don't you need a density function inside the integral?
Sorry?
Don't you need some kind of a density function inside the integral?
Well, that's what I have.
It's just one?
Yeah. Or if you like, I can write this as step function with PQ being inside my volume in phase space. Let me show you some weird symbol. You see, when you are calculating the volume of any object, you don't give different weights to a cube on the left-hand side and a cube on the right-hand side. Times d to the power 3 and p such that pi squared is less than or equal to 2e. This is the restriction on my momentum integral. So any questions up to here?
This P is the one with the bar elements, right?
Yeah. I mean, you can say
Square root of MIPI.
well, in fact, let me just keep this. By the way, this is not the correct energy expression. Well, for simplicity, let me keep mi to be constant. So this is the small p, and this is 2me.
I have a question. Is this gas contained in some container or is it free right now?
No, it's contained in I mean, all the systems we have will have a finite volume.
Right. So why do we take the integral over 3n? The volume is fixed. So why isn't it just dv?
Well, this is dV.
results in a V to the power n.
You see, let me, or if you want, let me just put it dv3n.
Yeah, but at most, all the particles are contained in that volume, so they can't escape it, right? So, I think İngilizcesine devam edemedim. Volümün kendisinin dışına çıkamayacağı için parçacıklar sanki o volüm belirlemeliymiş gibi integrate ediyor bana.
Well, let's do a more intuitive example. 2 dimensions. D to the 2 and Q. 2Q. Such that Qi, I being 1 or 2, they are restricted into this region. Okay. So this will be, you are right, it is a 2-dimensional volume. Well, in this case, the area. This is nothing but a square with side length L, which is nothing but L squared. L is just 1-dimensional volume of each one of those particles. This is for 3n is equal to 2. So if you want, well, this is the 2-dimensional volume in the 2-dimensional phase space. If you like, this is the 3n dimensional volume in phase space. It's not just the in 3-dimensional space, it's the 3n dimensional space. I can express that in terms of my volume in the 1-dimensional space. Well, that's what I do. Each one of those particles are confined into V. There are 3n of them. So the integral, or let me just write it slightly differently, what is d to the 3n cubed? d cubed q1, d cubed q2, d cubed q3, d cubed qn.
Yeah, but they're all confined in one finite volume, right?
Sure. So that which tells me that d cubed qi integral is just v. Well, here I have n of them. Each one will bring a factor v. So I get v to the n.
V to the n is the total.
Onu anladım. Ben niye 3 çarpı n artı 1 bir hypersurface'de çalışmadığınızı anladım. Neden 6n'e çıktığınızı çok anlamadım ama.
No, I'm not going to 6n. I'm only in 3n space, 3n momentum. Yeah. Well, that is my phase space. So you see, Q and P. What do I know is my particles are in this V3n. But my P can be along this line, let's say. So, but I'm looking at this 6n dimension, the volume of the surface area of that 6n dimensional space, hyperspace. So I have one volume, well, the volume integral is kind of trivial. And then I have another volume, which is due to this momentum dimensions, which I have to calculate in order to obtain this volume. Well, before continuing, let me take this expression. I haven't done anything yet. I just identified that this total number of states have to be proportional v to the n. Well, omega of E will be just derivative of E with derivative of the sigma with respect to E multiplied by possible uncertainty in E. But still this will be some function to the power v to the n times some function that depends only on the energy. I haven't yet done anything. The only fact that the energy of my system is independent of the volume already, or the energy is independent of the positions of my particles. You see, that is the assumption I make over here. I am already assuming that Q integrals do not change the energy, so the Q components are independent of the momentum integration. I have this expression as a consequence of that assumption. Well, the entropy is Boltzmann constant times the logarithm of this omega, which will be nkb times logarithm of v plus kb times logarithm of f of e Well, remember, the E was equal to TdS minus PdV. So if I take the derivative of entropy with respect to volume at constant energy, I'm not changing the energy, I'm just changing the volume and see how the entropy changes. Well, this will be minus P over T. This is just a thermodynamic definition. This is valid for any system. Derivative of entropy with respect to volume, if you keep the energy constant, is equal to the minus pressure over, no, plus pressure over temperature. Well, you can also see it from here. This is 1 over T times dE plus P over T times dV. Well, I can already take the derivative of this entropy expression with respect to the volume, keeping energy constant. Well, NKB over V, this is the derivative, is equal to P over T, and hence PV is equal to NKB times T. We already have the equation of state for the ideal gas. This is not an experimental observation, this is just a derivation we have. The critical things to obtain this result was to make this identification between the entropy and the number of microstates we have, and also the observation that the number of microstates can be written as V to the power n times some function of energy. You see, the number of since we are fixing the energy, the number of microstates is just the number of ways we can distribute the energy among all the particles we have. If the energy of my system doesn't depend on the position of my particles, just shifting one particle from here to over there will not change the energy. So in how many different points I can put my particle without changing the momentum of my particle? Well, I don't know the exact number, but the number will be proportional to V. So I can just change the position of each one of those particles without changing the energy of the system. And for each one of the particles, the number of different positions I can choose will be proportional to V. So if I have V to the n, there are V to the n possible positioning of the particles that will have exactly the same energy. That is why we have this V to the n factor over here. Of course, this will not be valid if there's an external potential. Changing the position of the particle will change the energy. So you won't be able to have this. Or if the particles' interactions are important. So if you just have many particles around, just look at one of them, you cannot just shift it around throughout the volume, because if it becomes closer to some other particle, it will change the energy of the system. So that is not a possible microstate. But for the ideal gas, okay, we are ignoring any external potential, we are ignoring any interaction between the particles. This is the result we have for the number of microstates, and hence we have the ideal gas equation of state. Any questions? Let's give a 10-minute break, and then we will continue.